So our next step here then, if we take a look at the diagram, is to figure out exactly where these different QoS policies are going to be configured, who is going to be doing the classification, who is going to be doing the remarking, and then where exactly the QoS policies are going to be applied on the service provider side. Now we have two routers that would be considered just C routers, just inside the customer network, that are not attached to the provider at all. These are router 7 and router 8. Where we have the customer edge routers, which are 1 and XR2, and then the provider edge 2 and XR1. The rest of the devices in the core, these are going to be the provider routers, or just the P routers. Now, specifically from the QoS policy point of view, what I'm going to be doing here on router 7 and router 8, on their ingress from the customer edge, they're going to be doing a QoS policy that is basically used just for accounting. So this policy is going to say, look for precedence value 0 and run a counter on how many of those packets are received. Look at precedence 1, 2, 3, 4, 5, 6, 7, etc. Now we could just as easily do this on DSCP values, because ultimately it's going to be the same bits that are inside of the IP header. But when we look at the customer to the service provider marking, remember that inside of the service provider network, the MPLS experimental bits, this is going to be the same size as the precedence, where we have values 0 through 7. So just to make it a little bit easier to read, I'm going to be using IP precedence on the customer side so that this will map on a one-to-one basis with the experimental bits. But you could just as easily do it with DSCP or whatever other markings that you want to. The logic is going to be the same. So then let's take a look at the configuration of these two routers, router 7 and router 8, to start. Where at this point the layer 3 VPN is pre-configured. On router 7, if we were to look at the show IP route, we're using OSPF as our provider edge to customer edge routing protocol, the PE to CE routing. And router 7 should be able to reach the address 8888, which is the loopback address of router 8. If we were to trace to this destination, we see that in the core, it's going through first to router 1, which is our customer edge. And then it goes from 1, 2, 3, 4, 5, 6. Then finally is exiting on XR1 before it goes down to the rest of the customer network, which is hops 8 and 9 here. So hops 2 through 7, this is the provider side. So we don't need to look at the details of the VRF or the BGP or LDP in the core. We know that we have transport between the sites. Anything beyond that point is going to be outside of the scope of QoS. Just want to make sure that we have basic connectivity first. So next on router 7 and 8, what I'm going to do is configure a basic QoS policy that is simply matching the traffic based on the precedence. So for the MQC implementation, there's always going to be 3 steps. First step is to classify traffic with a class map. Second step is to define the policy, the QoS policy, with the policy map. Then finally, the third step is to actually apply it with the service policy at the interface. So here on 7 and 8, I'm going to define class maps, and I'll say this one is going to be precedence 0. That simply says match IP precedence 0. Then we're going to have basically a class map for all the different precedence values. So then in the policy map, I'm going to be calling these individual classes, not actually applying any QoS, we're just calling them. And then we could use these as just a basic counter to figure out what type of traffic is being received from the other side of the network. So we're going to have classes that are precedence 0 through 7, match IP precedence 7. So if we show run section class map, or let's say show run class map, we should have 8 different classes. It's going to be 0 through 7. And this one, precedence 6, that should have just one match there. So let's say no class map match all precedence 6. redo that one and say match IP precedence 6. Okay, so again, 8 total classes matching precedence 0 through 7. Okay, next step is then to apply the QoS policy. This is going to be with the policy map. And we'll say that this is for matching the traffic. So I'm going to be calling these different classes, but they're not actually doing anything. So there's no additional QoS keywords under the class. I'm using just these as a counter, basically. Okay, another way that you could do this would be with IP accounting. If you went to the interface level and said IP accounting based on IP precedence, you could do that as well, but it's going to be a little bit easier to visualize when we use the QoS policy. So now on this link, fast Ethernet 00, which is that ingress interface here, we'll say service policy input is mark the traffic, or not mark, it was match. So if we look at the final result of this on router 7, we should have the 8 possible precedence values, which again you could just as easily use DSCP or some other classification, but it's going to be easy to look at this as compared to the MPLS experimental bits because it matches on a one-to-one basis. So the input policy, this is on the link facing towards the other customer edge. Now, what we're going to be checking here on router 7 then is the output of the show policy map interface fast Ethernet 00. And what I want to see is that on this link, what are, for the different classes, what are the different matches? So the number of packets, basically. And then we're going to use this just as a basic counter. Now, we will see that without changing anything else, I'm not generating any other traffic, there is going to be precedence 6 and 7, which is by default the control plane of the router. So some of the routing protocols, like OSPF in this case, is using precedence 6. If we were running BGP, some of the other control plane protocols, these are supposed to be for the network and the internet traffic. So you will see counters going up on these ones. The actual data plane packets, we're going to be using 0 through 5 to look at our markings. So basically this policy, I'm going to do the same thing on the other side. So this is on both router 7 and on router 8. So we're matching all the precedents, and then in on fast Ethernet 00, service policy input is to match. Now, to test this, one way we could look at the different precedence values, one of the ways would be with telnet traffic. So if I were to telnet to router 7 and then generate a bunch of traffic, let's say something like show tech support, it's going to generate a bunch of telnet packets. If I were to then go to router 7 and look at the output of that command, the show policy map, I should see that there is a bunch of hits now on precedence 6. This is the telnet traffic by default. You can also change this if you were to do an extended telnet, or if you were to say IP telnet type of service and then put in the value in hex of what you wanted here. Then you could change what the mapping to the IP precedence is. But by default, it's going to be using precedence number 6. Now, additionally, when we look at the MPLS core, so let me break out of this telnet session here. When we look at the MPLS core, who is going to be routers 3, 4, 5, and 6, if we look at the debug MPLS packets, we can see inside the layer 2 header of MPLS to figure out what are the experimental bits that have been imposed on router 2, and then what is the result of them when they are going to get disposed on XR1, when they're leaving the egress of the network and then going down to the rest of the customer network. So let's say we go to router 4, for example. And on router 4, we're going to look at the debug MPLS packets. And we should see at this point some control plane protocols. This is going to be like our BGP keep alives, some of the other control plane that's going on in the network. Most of these are going to have the experimental bits of 6 set. What this is showing us is that by default, when the router is doing the IP to MPLS imposition condition, it is automatically copying the precedence value from the layer 3 header to the experimental bits of the MPLS layer 2 header. So it's automatically doing the correlation for us to start. We do not need to configure a policy that says match precedence 6, set MPLS experimental 6. Match precedence 5, set MPLS experimental 5. The router, both in regular iOS and iOS XR, is going to automatically do this for us. Now, another way that we could see this would be to mark traffic as it is leaving the customer edge going out towards the provider. So in addition to this match policy that I have configured in on 7 and 8, I'm going to be configuring a mark policy that is changing the classification as traffic is leaving from the customer edge to the provider edge. And this is going to be done on both router 1 and on XR2. So both of the CE routers as the egress. Now, to tell the difference between some of the different flows, we can do this based on the different types of applications. So let's say some of the basic testing apps we can use. One would be ICMP pings. Another one would be Telnet. Another one may be TFTP. So basic flows that we can generate between router 7 and router 8 to see when we send those different types of traffic into the network, how does it get differentiated, and then what's the final result as it comes out of the other end. So let's then start this on router 1. And on router 1, I'm going to configure a couple different class maps. Let's say we have a class map that is ICMP that simply says match protocol ICMP. So on router 1, we're going to use nbar for this. We'll also have, let's say, telnet, match protocol telnet. And then let's say also TFTP. So match protocol TFTP. So 3 different types of flows that we can generate to figure out what are their markings when they get to the other end. Now, as this traffic is leaving the network, so outbound on Fast Ethernet 0/0, I'm going to configure a policy map. We'll call this mark that says for the class ICMP, set the precedence to, let's say, 2. For telnet traffic, let's set the telnet to 3. And let's set the TFTP traffic to 4. Then this is going to be applied outbound toward the service provider. Now, just to make sure that there's no other markings in the network, what I'll also do to make it a little bit clearer is that in the default class, let's remark everything else to 0. So we should only see 4 possible values, 0, 2, 3, and 4. So then on the Fast Ethernet, we'll say service policy output is mark. Then just like on router 7 and 8, we're going to look at the show policy map. Let's say show policy map interface Fast Ethernet 00. And I want to know how many packets are being marked. So let's say show policy map interface F00 include, let's say, class-map or marked. Okay, so our 4 possible classes: ICMP, Telnet, TFTP, and then default. Where again, these are going to be precedences 2, 3, 4, and then 0. Now, a quick way to test this then would be to go to router 7, and let's do some pings to router 8. We'll ping 8888, and let's say 100 times total. Okay, so 100 packets. If we now go to router 8 and look at the show policy map interface, Fast Ethernet 00, if the policy is working, we should see that there's a bunch of hits on precedence 2, which there is. So those 100 pings that I sent when they got to the other end, they did get received there as precedence 2. So this is telling us a couple things to start. Okay, first off, it means my classification and marking policy is working, which is good. But it's also telling me that the service provider core, by default, is not changing the customer's marking. So when we are performing the IP to MPLS imposition, and then the MPLS to IP disposition, these routers here are not changing anything in the IP header. Now we can configure them to do that. We could say match this, set this in a QoS policy, but the key is just that by default, the customer's marking is not being changed. As it's leaving as precedence 2 on this side, it's being received as precedence 2 on the other side. Which from a design point of view, the vast majority of times this is what you want. Service provider is really not going to want to be involved of what the customer's marking is. Okay, so next let's do the same thing on the reverse direction. So on XR2, as traffic is leaving, we're going to do the same type of marking policy. So I was using Telnet, TFTP, and ICMP. So on XR2, under the class maps here, if I were to say class map ICMP, we do not have the support for NBAR. So we can't say match protocol here. What we can do instead is call an access list that is classifying this traffic based on the layer 3 or layer 4 header. So before we have the class map here, let's also have some ACLs, which would be IPv4 access list. We'll say ICMP, says permit ICMP any. Access list telnet says permit TCP any equal to 23 or TCP any equal to 23 any. So I don't care what direction it's going, either client or server traffic. Then the TFTP, at least the initial portion of the TFTP is going to be UDP going to 69. The actual data transfer is going to be some random high port, but we don't need to catch all of it. We'll just, as long as we have the initial counter going, that's fine. So if we show config 3 access lists, ICMP, TFTP, and Telnet. And then next I'm going to have 3 different class maps. ICMP class map is going to say match access group ICMP. Telnet says match the Telnet access list. Then the TFTP says match access group TFTP. Okay, so now we have the traffic classified. Next step is that we're going to mark the traffic. So just like in regular iOS, we have the policy map. So policy map mark says for class ICMP, set the precedence, and we're going to set this precedence to 2, same as the other side. And then for Telnet, we'll use precedence 3. For TFTP, we'll use precedence 4. And then for everything else, which is the class default, we're going to set the precedence to 0. So you can see that the syntax is fairly close to the regular iOS. So as long as you understand the regular enterprise QoS in regular iOS, then it's going to be the same on the iOS XR here. So then our final step would be to apply it to the interface. And I want this on XR2 to be applied on the egress interface towards the PE, which in this case is POS 0700. So let's say on interface POS 0700, service policy output is to mark the traffic. And then let's commit that. Now what the final result of this is going to be is that when we go to router 7 or router 8 and look at those counters in the policy map, we should now be seeing either precedence 0, 2, 3, or 4. So on both of these, let's say clear counters, that'll reset the counters for the policy map. Clear counters. We should see now that the pings for ICMP should be hitting precedence number 2, which they did, 5 packets on precedence 2. 5 packets on precedence 2. We then had the telnet. So if I was to telnet to 8888, generate some traffic, then look at the policy map. We could see that's precedence 3. Then if we were to generate some TFTP traffic, that should be precedence 4. So let's say on this router, we'll serve the iOS image. So let's say TFTP server from Flash, the iOS image. Then on the other side, on router 8, let's say copy TFTP remote address 7777, the image name, and then copy it to null. So we're just discarding the packets. Okay, once we get some traffic generated there, and then we look at the show policy map again, we should see that was precedence 4. So again, now we know that the marking and the matching is working. This also again means that in the service provider core, it's not changing the router's or the customer's classification and the marking. Now, if we take a look at the core, previously on router 4, I was looking at the debug MPLS packets. And this is still outputting to the console here. I probably should have turned this off before. But one thing that we will notice, let's undebug, is that the TFTP traffic, which we were changing to precedence number 4, this is being maintained inside the MPLS experimental marking. So it's that number in the middle, which again means that on the IP to MPLS condition, or the IM position on router 2 and on XR1, it's automatically copying the customer's marking into the service provider network. So if you don't want to change the customer's marking, you don't need to change anything else. It's going to happen automatically. But normally what you would want to do in a real design here then is to match the different types of traffic coming from the customer and do some sort of queuing policy with it. So let's say, for example, now that as the traffic is being received in from the customer, we want to apply some sort of service level agreement with them. Let's say that for the TFTP traffic, let's say that this is our bandwidth hungry application. So we want to do a bandwidth guarantee. And for let's say the telnet is going to be like our real-time applications. So we want to put this into a low latency queue or a priority queue. Now we know in order to do this that the QoS has to be end-to-end. That if we're doing the admission control on router 2 on the provider edge, we need to make sure that on the P routers in the middle that we're also enforcing this. So it's going to have to be on all of the egress interfaces basically in both directions. Now we don't really need to do this for every single one everywhere. Once you see the example on one of the routers, it's going to be the same logic on the other ones. But let's take a look at this from router 2's perspective. So for the TFTP traffic, I want to do a bandwidth guarantee, and let's say we do a guarantee of 1 megabit per second. And let me list this separately on the whiteboard so we can keep track of it. So TFTP, this is going to be our bandwidth guarantee. And we'll guarantee 1 megabit per second. Then for telnet, we want this to be in the low latency queue. This is going to be the priority queue. And let's say we give it 2 megabits per second of priority. Then the ICMP traffic, we'll say that this is going to be our scavenger class. And let's say that for ICMP, we're going to accept, let's say, 256 kilobits per second. And we're going to accept that unmodified. If you go over 256, let's say from 256 to 512, I'm going to remark this from EXP2, which it currently is, from 2 down to 1. then anything above 512, that's going to get remarked to 0. So it goes down to the best effort class. So we're going to be using a 3-rate policer here: the conform, the exceed, and then the violate actions. So first, let's look at doing the TFTP with the bandwidth guarantee. Again, the experimental bits that we used here were 2, 3, and 4. So TFTP is experimental 4 or precedence 4. Telnet is precedence 3. ICMP is precedence 2. Now again, as the traffic on router 2 is getting imposed, so we're adding the MPLS labels, we have automatically copied IP precedence 4 for the TFTP. We've copied 4 to MPLS experimental 4. This means that when we actually go to do the bandwidth guarantee, which is going to be on the egress interface towards the core, okay, so this fast Ethernet subinterface, we cannot match on the IP packets, because by the time the traffic gets to the outgoing interface to the QoS classifier, it's no longer native IP. It's going to be labeled MPLS traffic. So this then means that we need to match based on the MPLS experimental bits. Now, just like the other policies that we configured, it's going to be the same 3-step process. So on router 2, we're going to have a class map. We'll say that this is MPLS experimental MPLS experimental 2, or excuse me, not 2, that was 4. That says match MPLS experimental. So look at the topmost label in the stack, and I'm looking for number 4. Okay, I then have a policy map that is going to be out to the core, let's say, or out to the P routers. Okay, so the P routers are the core. For the class MPLS experimental 4, I want to do a bandwidth guarantee. And I'm going to do a bandwidth guarantee of, what did I say here? It's going to be 1 megabit per second. So bandwidth of 1,000 kilobits per second. This is then going to be applied on the egress interface towards the core, which is interface F00.23, service policy out to the P routers. Okay, service policy is not supported on subinterfaces. On some of these lower level platforms for the regular iOS, when you're doing egress queuing, since the Ethernet subinterface does not have its own hardware queue applied to it, this would just have to be applied to the main interface. From our point of view, it's not going to change anything though, because when we look at the physical design of the diagram here, there's only one link that is using that main interface, fasting it at 0/0. So anything going out the main interface is automatically going to be anything going out that sub interface. You'll see that most of the input QoS features like input policing or input marking, you can do those on sub interfaces, but some of these platforms have hardware dependencies on where you can apply it. And it's simply going to tell you you can't do this. Okay, if it was going to work, it wouldn't give you that error message. Some of them, as well as a workaround, if you were to also put a shaper on here, the shaper would automatically create a software shaping queue. Then you could apply the bandwidth reservation onto the shaper, but we don't really need to do that here. Applying it to the physical interface is going to be the same final result as if it was applied onto the sub interface. So now if I were to look at the show policy map interface fast Ethernet 0/0, and I want to know, is anything actually matching this experimental 4 as it's going out? So to check this, let's try transferring that file again. So copy the TFTP file. If we now look at router 2 and look at the policy map, we can see now there's a bunch of packets that are matching experimental 4. So when you're looking at the final result of these QoS policies, you need to make sure to look at the show policy map and see that the counters are going up. If for some reason it didn't show that we're actually getting any hits here, most likely it means that your policy is not configured on the right interface, or you're doing the wrong type of classification, like you're supposed to be looking at MPLS when you're looking at IP. But this is a pretty surefire way to see that this is actually working. That on the topmost label number 4, or not number 4, experimental number 4, that the packet counter is actually going up. Now, if we were to finally trace this along the path as it exits and gets towards XR1, okay, so it's going in this direction, it finally gets to XR1. Let's say that we want to maintain this policy end to end. So not only do I want to guarantee 1 megabit per second as it is transiting the core. So basically I would do the same exact policy I did on router 2, apply that on 3, 4, 5, and 6, and it's going to do the same thing. But now the issue is that when it gets to XR1, and I go to schedule the traffic on the POS interface down towards the customer, am I looking at the MPLS traffic, or am I looking at the native IP packets? If I'm looking at the MPLS packets, this is going to be easy to classify because I already know that this is supposed to be marked as experimental 4. But if this is the IP packet, I don't want to have to do the same classification in the reverse direction. So really, most of the time, it's going to be up to the customer to do their own marking. Like to say that my phone call, my voice over IP phone calls are going to be DSCP-EF, and that the signaling of the call is going to be CS3 or whatever other marking that we want to do for this. Then the service provider is going to say, this is what my policy is going to be. If you want to conform to this, it's up to you to match my classification policy. But now the issue is that if XR1 wants to extend this QoS onto the last hop link, how do we do the classification? And this is where that special placeholder comes in, which is going to be the QoS group. So let's look at this first on XR1, trying to do the same type of classification that router 2 was doing. We're on router 2. If we look at the show run section class map or policy map, the class is saying, look at experimental 4. If it is experimental 4, then give it a bandwidth guarantee of 1,000 kilobits per second. Then out to P, that's being applied onto the interface towards the core. So let's do the same thing on XR2. If I were to say that on this router going towards the customer, we have class map that is MPLS experimental 4. So on XR1, not on XR2. Class map, MPLS experimental 4, match the experimental 4. Then we have the policy map. We'll say that this is out to the CE. For class MPLS experimental 4, I want to do some sort of scheduling for this. So if we look at the QoS options here, they're fairly similar to what you have in the regular iOS. So if I wanted to do a bandwidth guarantee, let's say 1,000, and then what's the unit? The unit kilobits per second is going to be default. Then on the actual link that's being used, which is this one here, POS 0600. POS 0600. We'll say service policy output is out to the CE. Then let's show config, look at our result. So fairly straightforward policy. We're just looking at the experimental bits, saying if it's number 4, give it a 1 megabit per second guarantee out towards the customer. Now, once we commit this, we can see it didn't give us an error message, so there was no commit failure. If we look at the show policy map interface POS 0600 for the output policy, ideally I want to see that the traffic is matching and that it is either getting transmitted or dropped. Whether it's sent or dropped is going to be based on like the length of the queue, and in this case we're just doing tail dropping. So we could configure like weighted random early detection if we wanted to do red for the emission control, but by default it's going to be doing tail drop. My key is that I want to make sure that this is actually getting matches. So to test this, let's look at the same transfer as before. So we download that file. On XR1, when we look at the show policy map, either this traffic should fall into class experimental 4 or class default. And the counters are not real time here, so you have to give it a little bit to actually apply. Okay, this result, this is bad. What this means, you can see that the packet counters, this is happening on class default. It means that on this interface, when I tried to classify as experimental 4, it's too late to do this because I already performed my MPLS to IP disposition. So out towards the customer edge, it's too late to classify based on the MPLS header. It means I now need to classify based on the IP header. But again, the problem then is you're asking the service provider to maintain this complicated policy where they're not going to want to have access lists, or they're not going to want to have like N-bar in order to do classification for the customer. So then how do we solve this? How do we get the experimental 4 as it comes in on this interface to be dequeued on this link based on what the service level agreement is? And the service level agreement says give it 1 megabit per second. And the way to do that is that placeholder that is the QoS group. So what we're going to use the QoS group to do is to look for experimental 4 as the traffic is coming in. If the traffic is experimental 4, I'm going to set the traffic to the QoS group. We'll say, just for clarity, we'll use QoS group 4. Then as the traffic is leaving POS 0600, we're going to match QoS group 4 and then put it into whatever we want to do for scheduling. Are we doing bandwidth guarantee, prioritization, weighted random early detection, whatever normal QoS policy that we want to apply. But the key now is that we're not doing a remarking of the customer's traffic. So we're not changing what was there originally. We're just using the QoS group as a temporary placeholder between the local interfaces on the router. So this means then we need a new input policy on XR1, and we're going to have to change our egress policy, or the output policy. So here the input policy then needs to be applied on this subinterface, which is going to be the gig 0100.619. That's for the traffic as it's coming in from router 6. Now if we actually look at this traffic on router 6, let's go to 6 and say debug MPLS packets. If this were a ping from 7 to 8, we should see that this has the marking, and actually am I still downloading? Yeah, I'm still downloading that file. So on router 6, again, we're looking at the debug MPLS packets, and then let's do a ping from 7 to 8. What we should see is that in the experimental bits here, this is using number 2. Now notice what's happening as the traffic is transmitted out towards the provider edge. And let me undebug all here first. The interfaces that are being used are fast Ethernet 00.56. This is going towards router 5. From 5, the packet is going to 6. Then from 6, the packet is going to XR1, which is the PE. So it's coming in .56. The RX means it's received. It's being transmitted to .619, which is towards XR1. And notice that there's only now one label in the stack. This again is because router 6 is doing the pin ultimate hop popping, or the PHP process. It's removing that topmost label and sending just the VPN label underneath. Now in this case, it doesn't really affect our QoS design. It's no problem that router 6 is doing the PHP process. But if for some reason I was changing the experimental bits of the transport label in the core, I may want to configure router 6 to not depose the topmost label before it is going to the provider edge. And that's what I mentioned before is the ultimate hop popping, not the pin ultimate hop popping that you would configure on the PE under MPLS LDP. You would say to use the explicit null label. And in regular iOS, if we were to go to router 2 and say MPLS LDP explicit null in global config, that's going to mean the same thing. So now if I were to go to what used to be the pin ultimate hops, the pin ultimate hops used to be 6 and 3, and look at the show MPLS forwarding table, when we look at the loopbacks of the connected neighbors, like of router 2, it says now we're using the outgoing label explicit null as opposed to implicit null or pop label. On router 6, if we do the same thing, show MPLS forwarding table, this is going to be for 19, 19, 19, 19. This now has explicit null. What is now going to change if we look at the debug MPLS packets and then send traffic between the customer sites again? So if we send a ping, we would see now that the topmost label is not deposed, but instead it's assigned a label value of 0. And the key here with this 0 label, which is the explicit null, it's maintaining the MPLS experimental bits that were used in the transport label for the rest of the core. So again, for this example, I'm not changing the transport label for anything, so it's not really affecting the policy. But if you did want to maintain it end-to-end, that's the reason that you would want to turn on the explicit null, or essentially the ultimate hop popping on the edge. Okay, so let's go back to XR1. Let's change the policy then in order to use the QoS group. What I need to say here then is that as the traffic comes in on gig 0100.619, look for the experimental bit values. And we already have that called in a class map. So let's say show run class map. I already have experimental 4, so I can reuse this class. Now I have a policy that is going to be in from the P routers that says if it is class MPLS experimental 4, set the QoS group to 4. Then this is applied on that link as an ingress policy. So service policy input in from P. Then I need to change my current policy. So let's say show run policy map. The one that is going out to the CE, I no longer can call MPLS experimental 4. I now need to call QoS group 4. So I now need another class that is going to be class map QoS group 4 that says match QoS group 4. In policy map out to the CE, I'm not calling class MPLS experimental 4. I'm calling class QoS group 4, and then doing whatever QoS that I want. In this case, I'm applying the bandwidth reservation. So if we look at the full change in the show config, there's two classes, one matching the experimental, one matching the QoS group. I'm saying as it comes in from the core, if it already is experimental 4, which we know it's going to be based on the debug MPLS packets we already saw, set the QoS group. Okay, this is the placeholder here. Then as the traffic moves to the interface going to the customer, I'm saying check for that placeholder. If the placeholder's there, then put it into whatever specific queue that we want. So now once we commit this, and again look at the show policy map on the interface, I want to see for QoS group 4, now do I have matches on the counter. So let's download that same file again. And 6 is still debugging. I should have turned that off. But now in XR1, let's look at the show policy map on the interface. We should see that in a minute after the counters update that we're going to get hits here, but not as many hits here. Which we do. We can see now the traffic is matched in QoS group 4 and then ultimately getting into that specific output queue. So in order to form an entire policy that would do this, what we would need to do is manually match essentially all of the experimental bits as they come in, set these to different QoS groups, and then apply those on the egress interfaces down towards the customer. So we could take this type of example policy that we have on XR1 here and then edit it to match all of the other possible values that we need. So let's say that we have all of the QoS groups. So not only 4, but we need 0 through 7. So we would have all of these values, QoS group 0, 1, 2, 3, etc., all the way up through 7. Then we're saying, as the traffic comes from the core, check for the corresponding MPLS experimental. If it is MPLS experimental 1, then set the QoS group to 1. So we need more of these classes as well. Experimental 0 to 0, 1 to 1, 2 to 2. Now you'll see that depending on the direction that you're doing the match in the set, you'll have the option to set MPLS experimental topmost or to set MPLS experimental in position, where the difference is, are you setting just the transport label, which is going to be the topmost label, or are you setting the transport label and the VPN label at the same time? Where the VPN label, that's going to be the in position one, the transport label is going to be the topmost one. And again, you'd be able to see that regardless when you look at the debug. How many labels deep is the stack, and then what are the numbers in the middle? Those are the experimental bits. Okay, so now we have the policy that says look for QoS groups 0 through 7. Look for MPLS experimentals 0 through 7. Then the policy says from the provider routers, if it's experimental 0, set QoS 0. If it's experimental 1, set QoS 1. 2 to 2, 3 to 3. So it's not going to do this automatically for you. If you want to enforce this type of marking, you have to manually configure the policy. Which makes sense because then it gives you more granular control over exactly what's going on with these values. Because QoS groups 0 through 7 here, they're technically any arbitrary number that I'm using. But once I were to apply this, so now let's add all of these in on XR1. So the show config, we should see all the classes for the QoS groups, all the classes for the experimentals, and then the correlation between the two of them. So let's commit this. This is basically what you would want to stage on all of the PE routers. So on the links that are facing towards the core, you apply it inbound. Then on the links that are facing towards the customer, that's going to be the actual QoS that is applied out to them. So now the only thing the service provider needs to say is that if you want priority traffic, send me your traffic with IP precedence 5 or send it to me with IP precedence 4, because I can correlate those values throughout the core of the network. Then when it ends up on my PE, I'm going to know what particular value to look at and then how to send it into the priority queue. So if we look at what those mappings I was mentioning as before, let's say next that we want the telnet to be the low latency traffic. And the telnet is using precedence number 3, which is automatically correlated to experimental 3. So now on the ingress, which is router 2, okay, assuming that the traffic is going in this direction, on the ingress of router 2, I don't need to change anything, because when I'm doing the IP to MPLS imposition, I'm automatically copying precedence number 3 in the IP header to experimental 3. Then it goes all the way to the egress. It goes to XR1. And then once it gets there, I can just say, look for QoS group 3. I now have it in the egress queue, and I can do whatever I want with it. So if we were to go to XR1, and configure a new class that's going to be under the policy. Let's look at the show run policy map. This is going to be out to the CE. That it says for out to the CE, if the traffic is class QoS group 3, put it into the priority queue, and I'll give it the first level of priority. So in XR, you have multiple priority queues. But then I probably also want to limit it at the same time. So by default, iOS XR does not have a policer built on with the low latency queue. So I'm going to give it strict priority, but I'm also going to police it. And I'm going to police it to a rate of 2 megabits per second. Then the conform is going to be transmit. The exceed, I could drop the traffic, or I could say if I exceed, then I'm going to set the QoS group, because now it can't be MPLS experimental. I'll set the QoS group down to 0. So this doesn't mean that I'm going to drop the traffic. It just means that it's going to have a lower priority. You could really do it either way. If I wanted to say just flat out don't prioritize the traffic and drop it, then the exceed action is going to be simply drop. Okay, but just like in regular iOS, you could do it however you want to. Okay, it says the complete police conform rate is adjusted to 1984 to meet the hardware supported precision. So it's rounded to whatever value that it needs there. It's probably multiples of 8. Then if we look at the, let's say, show run policy map, so we're policing to 2 megabits per second, and we're giving it prioritization. If we now say show policy map interface POS 0600 output, I want to see now if I do the telnet, is it getting into QoS group 3, and is it getting prioritized? So I'm not sure if we can actually generate that much telnet traffic, 2 megabits per second, but if we were to go to router 8, and let me make sure I'm undebugging in the core. If I were to go to router 8 and telnet to 7777, let's say show tech support, so it's generating a bunch of telnet traffic. If we now look at this counter, show policy map on the interface, ideally those packets should automatically be correlated to QoS group 3, which they are. So again, beyond the normal QoS that you would already have in the enterprise, the big thing with applying this onto the service provider network and specifically to MPLS is that you need to know when you're doing the classifier, are you supposed to be looking at your native IP packets? Are you supposed to be looking at the MPLS packets? And if you are looking at MPLS, what level of the label are you trying to look at? Are you trying to look at the topmost label, or are you trying to look at the bottom label, which is going to be the one at the imposition? Now, if you do want to get more information about this, a couple good resources to take a look at. One of them is going to be the kind of the standard book for QoS on for Cisco's implementation, which is the QoS exam certification guide. This one is part of, I believe this is part of this CCVP for the voice certification. But the other one is specifically QoS for IP and MPLS networks, which talks more about the correlation between the experimental bits and the IP packets. Goes through some examples of the different modes, like the uniform mode, the pipe mode. Then there's some other minor variations like short pipe, long pipe. But again, the idea with those modes is that in pipe mode, whatever comes in on one end of the customer network is the same that is sent out on the other end. So nothing is going to be changed. With the uniform mode, whatever the marking that the customer has, that's copied to the service provider network. If the service provider changes something, it means that that is then going to be copied back down to the customer.